Okay, good evening, children. Uh, Today, here we are with nucleophilic addition reaction, a very important reaction for aldehydes and ketones. We know that in aldehyde and ketone, this carbonyl group is there. So there is a carbon-oxygen double bond, though not carbon-carbon double bond, but nevertheless, there can take place addition reaction, and the addition reaction is nucleophilic addition reaction that we are going to see here. Now, carbonyl group has resonating structure, and because of this pi bond electron going towards more electronegative oxygen, so there will be plus charge on carbon and minus charge on oxygen. So these are the two contributing structure of carbonyl group, and its resonance hybrid is this. So this resonance hybrid shows that carbonyl group is polar in nature, with positive charge on carbon and negative charge on oxygen. So this you need to remember, because nucleophilic addition reaction will be due to this polar nature of carbonyl group. So what is nucleophilic addition reaction? It is like this. First step, nucleophile which is rich in electron, since it looks for positive center, and positive center is here. So positive center is here, we can see from here. So this comes and attacks at this carbon, and due to that the pi bond will break and come over oxygen. So this is the first step, and due to that what will happen is due to that this oxygen will become minus, and now there occurs also change in hybridization. In carbonyl group, this carbon atom is sp2 hybridized. This carbon atom is sp2 hybridized. So this unit is planar, and because of nucleophile attacking, there is change in hybridization with this carbon. Now it is sp3 hybridized. Okay, and in the second step, the first step, in the second step, what happens is from water, a proton from the water gets attached to this O minus, and we get the product NuOH. So this is the product of nucleophilic addition reaction. Why it is called nucleophilic addition reaction? Because this reaction is starting with a nucleophile, and that's why nucleophilic. And you see, if you see the product carefully, you will see what has happened is, at carbon nucleophile is added, at oxygen H is added. So that's why it is an addition reaction. Addition has taken place across carbon-oxygen double bond. Here Nu has come, here H has come. So this is addition product. Okay, now it is found that very important statement, aldehydes are more reactive than ketones. So this is a very important question which also comes in exam. Aldehydes are more reactive than ketones. Like, how to explain this? Now, you know that aldehyde aldehyde is this unit, and ketone is this unit. Ketone is this unit. This is aldehyde, and this thing can be explained. We can give two reasons for this. The first reason is called the electronic reason. Electronic reason, and according to the electronic reason, what happens is that since alkyl group has plus I effect, so the delta plus charge at carbon, where there is a slight positive charge at this carbon, this delta plus charge, the positive charge at this carbon gets decreased because of electron flow. Because of electron flow, the positive charge gets decreased, and because of decrease in the positive charge, nucleophile will get less encouragement to attack at this place. Nucleophile will not attack so readily at this place. On the other hand, in case of aldehyde, there is only one alkyl group, and there is only one alkyl group. So here also there will be slight decrease in the positive charge because of plus I effect. But ultimately, positive charge at this carbon will be more than at this carbon. Positive charge at this carbon will be more, and as a result, the nucleophile will more easily attack in case of aldehyde. So that is the reason why aldehydes are more reactive than ketones, and this is what is known as electronic reason. We can give another reason to this explanation, that is a steric reason. And what is steric reason is, it is said that since here there are two alkyl groups, and alkyl groups are bulky, so this nucleophile will experience some steric hindrance, whereas this hydrogen, being very small in size, in this case the nucleophile will not experience such hindrance. The nucleophile can easily come and attack here. Here nucleophile will not find it so easy to attack here. That's why ketones are less reactive than aldehyde. And this is what is known as steric reason. So with the help of these two reasons, electronic reason and steric reason, we can explain that aldehydes are more reactive than ketones. Okay. Now aldehydes, aldehydes can be aliphatic and aromatic. Aliphatic and aromatic. Aliphatic and aromatic. I'm giving you one example in each case. Aliphatic aldehyde is HCHO or CS3CHO. These are aliphatic aldehyde. And example of aromatic aldehyde is, say, this is an example of aromatic aldehyde, benzaldehyde. Now, it is seen that aliphatic aldehydes are more reactive than aromatic aldehydes. So these also can come in exam as a question, explain why type of question. So aliphatic aldehyde are more reactive than aromatic aldehyde. Why? Okay, now aromatic aldehyde, there occurs resonance. Let me draw the resonance structure. So here what will happen is uh, there will be minus R effect. Minus R effect will be there. Because of that, this bond will come here. This pi bond will break, will come here. So the first structure that we will get is so a double bond here, carbon, single bond O, and here 2 electrons, 3 lone pairs, minus and H. And as a result, this will be plus. So this one, then another structure that arises will be this one will come here in the next, and nothing more, only this one coming here. So because of that, and the next case what will happen is this one will here. Then a positive charge will be developed at this place. So these are the resonance structure, and due to this resonance, what is happening is that you can see this positive charge on carbon, the positive charge which is on carbon here, that positive charge is going to the ring carbon atom. That positive charge is going to the ring carbon atom. So if positive charge of this carbon is going to the ring carbon atom, so positive charge here will decrease, or here positive charge will be less. So that's why aromatic aldehydes are less reactive. Whereas in case of aliphatic aldehyde, say this one is aliphatic aldehyde, here there is no resonance. Here there is no resonance, and that's why here such decrease in positive charge is not happening. That is the reason why aliphatic aldehydes are more reactive than aromatic aldehydes. Now we will give some particular example of nucleophilic addition reaction. Okay, so nucleophilic addition reaction we will discuss under these 5 heads. One is addition of HCN, second is addition of sodium bisulfite, third is addition of alcohol, fourth is addition of RMGX, Grignard reagent, fifth is addition of ammonia derivative. So let us do first number 1, addition of HCN. So suppose this is an aldehyde or carbonyl group unit as HCN. Now this reaction is catalyzed by a base. This reaction is catalyzed by base. What actually happens is this HCN plus base, this base accepts this proton, so it becomes BH plus and CN minus. So nucleophile is generated by the base, and after that what happens is this nucleophile it attacks at this place, and simultaneously this goes here, and it becomes and it becomes O minus, and in the next step the next step, this H plus will come. Okay, I am writing step by step. And the next step, H plus, it can come from the solvent water or it can come from HCl. And it is forming this. So this is the product. Now, a compound where the CN and OH attach to the same carbon, they are called cyanohydrine. Cyanohydrine. It is important because many other types of compound can be prepared from cyanohydrine. So that's why this compound has got synthetic utility. Okay, and so let us do the next case, that is addition of sodium hydrogen sulfide. So suppose for this we take say acetaldehyde. Acetaldehyde we take. So this sodium hydrogen sulfide, sodium hydrogen sulfide, and here what is formed initially is so here what is happening is this unit SO3H, this SO3H is acting as nucleophile, and the nucleophilic site is S. The nucleophilic site is S. It is attacking through S. So here SO3H is formed and O minus Na plus, and you know this. These steps are reversible. And the next step, what happens is there occurs a proton transfer. The reason for proton transfer is sulfonic acid. You know, if a strong acid, it will like to exist as anion, it being a strong acid. So H plus from here will come here. H plus will come here, proton transfer, and simultaneously this Na plus will go here. So due to proton transfer, we have this CH3H, SO3 minus Na plus, and here OH. So this is called sodium bisulfite addition product, and you know this is formed as a white crystalline precipitate. A white crystalline precipitate. Okay, now suppose this is an acetaldehyde. What can we name this product? We can name this product as an acetaldehyde sodium bisulfite addition compound. The name of this is acetaldehyde sodium bisulfite addition compound. Okay, now we can make use of this reaction. We can make use of this property of aldehydes or ketones to separate to separate carbonyl compound from non-carbonyl compound. So suppose you are asked how will you separate a carbonyl compound from non-carbonyl compound. So that mixture of carbonyl compound and non-carbonyl compound will be treated with sodium bisulfite, and only the carbonyl compound will react, the other compound will not react. So what will happen is carbonyl compound will give a white crystalline precipitate. The non-carbonyl compound will not give the precipitate. It will just get separated. And finally, if this white crystalline precipitate is treated with acid or base, we will get this compound. That means we have separated a carbonyl compound from non-carbonyl compound, and we also have recovered back the carbonyl compound. This thing we have to note that these steps are reversible. That's why on treating this with acid or base, we get the starting carbonyl compound. Okay, now let us discuss the third reaction. That is addition of alcohol. So addition of alcohol, suppose this is an aldehyde, this is an alcohol, and this reaction takes place in presence of dry HCl gas. And here actually what happens, this is a nucleophile unit that attacks, and after the attack, this thing happens. This H part gets attached to O minus, and you see this is a ethyl functional group formed, and this product is called a hemiacetal. Now this hemiacetal can further react with another molecule of alcohol, again in presence of dry HCl gas. And how this reaction happens, I am showing it to you here. That R dash OH, there will be this H and this OH will combine to form water, and this another ethyl unit is formed, and this removal of this water is getting precipitated by dry HCl gas. Dry HCl gas absorbs this water that is formed, and this molecule having two ethyl group attached to the same carbon atom, this is called a acetal. So the product of addition of alcohol to carbonyl compound is a acetal. Now suppose how will you name this compound if you are starting with acetaldehyde. Okay, if you are starting with acetaldehyde and suppose this is methyl alcohol, if it is acetaldehyde, this is methyl alcohol, then we will get the product. We will get the product like this. And the name of this compound will be acetaldehyde, and the name of this product will be acetaldehyde dimethyl acetal. Okay, now since we know that ketones are less reactive than aldehyde, for this reaction to happen with ketone, we have to take a dihydric alcohol. In this way, suppose we take a ketone, suppose CH3, C double bond O, CH3. So ketones cannot react with monohydric alcohol. For ketones to react, then it should be a dihydric alcohol. So this is a dihydric alcohol. This is ethylene glycol. So how this reacts, you can easily understand this oxygen unit, this H unit, this H unit, they are involved in the loss of water and this is formed. If I use this only, so it will be CH3, CO, this is CH2, CH2, O, yes. So this is formed from ketone. Now the formation of hemiacetal, the formation of or acetal also enables us to separate a carbonyl compound from a non-carbonyl one. Carbonyl compound will give this acetal, non-carbonyl compound will not give this acetal, and on treating this acetal with acid, we will get back the starting aldehyde. So children, let us do today till this reaction. In our subsequent classes, next class, we will be doing point number 4 and 5. Till then, good night.